Let's take a look at the last two problems. So we see that in this problem, we have a fish hanging from a scale, and that scale is in an elevator. And we want to find the apparent weight of this salmon when the elevator is at rest, when it moves upward, and when it moves downward. So the first thing we should do is set our coordinate system. And so here is going to be my y-axis, here will be my x-axis. And I hope you can immediately see that nothing is happening along this x-axis. This fish is not moving in this direction or that direction, but it is moving either upwards in the positive y direction or down in the negative y direction. So when we consider how to start this problem, let's think about all of the forces that are acting on this fish in the y direction. Well, this fish has an apparent weight and it also has an actual weight. So the sum of those forces in the y direction is going to be that apparent weight minus the actual weight. And we say minus because the weight is pulling this fish down in the negative direction. Well, we want to solve for the apparent weight. So this would become apparent weight equals the force in the y direction plus the actual weight. Okay, now we can go back and actually plug in some information that we know. This is equal to mass times, that should be an A, mass times acceleration plus mass times gravity. Well, we see mass twice, so we can pull that out to find that our apparent weight is mass times acceleration plus gravity. In part A, we see that the elevator is at rest. That means acceleration is 0, and the apparent weight is just going to be equal to the mass, which is 5.2 kilograms, multiplied by gravity, which is 9.81 meters per second squared. So the apparent weight when the elevator is at rest is going to be 51.0 newtons, and that is in the y direction. Okay, so that's part A. Y'all go ahead and try part B and play the video when you're ready. Okay, so for part B, you should have found that the final answer, the apparent weight, is 69 newtons, and that is also in the y direction. And for part C, you should have found that that apparent weight is equal to 39 newtons, again in the y direction. And the difference here is that we see in part 3 there's a downward acceleration, which means this 2.3 needs to be negative. So that's how you solve for A, B, and C. Okay, go ahead and erase that. And the final problem, we are not working with any numbers here. We're just going to work with the variables. So we have a child of mass m who's riding down a slick ice-covered hill. So that slick ice-covered hill indicates that there's no friction involved. We're going to ignore it. At an angle theta with respect to the horizontal. And we want to know the acceleration of that child. And then we want to know the normal force that's exerted on the child by the toboggan. So I'm going to draw my picture here. That's going to be my hill. This is my little toboggan. There's a kid on this. Oh my, this is a very bad drawing. Okay, there's the kid. And before I do anything else, I'm going to go ahead and draw my coordinate system. So I'm going to make the coordinate system where the x-axis is parallel to the surface. Okay, so I have my positive y going up and my positive x. Obviously, these two don't matter because we're not moving in the negative direction at all as this child is moving down the hill. Now that we have that, let's think about the forces that are acting on or that are present in this system. So we have a normal force, and remember the normal force is perpendicular to our surface. So put it here, and it's going to be perpendicular. And that is the normal force. And we also have the force of weight, which is just going to go straight down. So the weight will be here. Okay. That means the total sum of our forces is going to be that normal force plus the weight. Okay. But let's consider a couple of things before continuing. First of all, is this child moving along the y-axis? No, this child is moving in the positive x direction. So that means we are only going to need to pay attention to what's happening in the x direction to find out the child's acceleration. There is no acceleration happening in the y direction. Well, if there's no... Well, hold on. Okay, so we want to pay attention to what's happening in the x direction because that is the direction of acceleration. So let's take a look here. Okay, we have drawn our system, so let's see if we can simplify this anymore. The normal force is only pointing perpendicular to the surface. So in this instance, it is only in the y direction. This force right here is only in the y direction. So this can be completely ignored. This is just going to go to 0. That means the force in the x direction is just going to be equal to the force of the weight. Well, to solve for that, we will need to recall a few pieces of information. So the sum of those forces is 0 now. We're going to ignore this. Plus the force of the weight. I'm sorry. But we only want the weight in the x direction. And remember, to find this in the x direction, you're just going to take the weight and multiply it by sine theta. And weight can be rewritten as mg. So I'm going to write mg sine theta equals, okay, we know that force is just ma. So that means mg sine theta is equal to ma. Okay, so we want to solve for acceleration. You will plug in all of the information that you need, which we already have because we don't have a mass, it's just m, and we don't have theta, it's just theta. So your final answer is just going to have a bunch of variables in it, and our m's cancel out, leaving the final answer as g sine theta. So that would be the acceleration of the child. Okay, now what is the normal force exerted on the child? By the toboggan. So we want to know the normal force, the one in the y direction. Obviously, it is 0 in the x direction. So pause the video and try this yourself. Play when you're ready. Okay, to solve for the force in the normal force. Sorry, I should have erased all this. Since we are solving for the normal force, we only care about what's happening in the direction of the normal force, and in this case, that is what's happening in the y direction, the positive y direction. Well, the y direction in general, I'm sorry. So let's do this again, except this time, we're going to be looking at the sum of the forces in the y direction. So the normal force is in the y direction plus the weight that's in the y direction. Well, just like we did with the weight in the x direction, let's substitute this because the weight in the y direction is equal to the weight, which is mg, multiplied by cosine theta. And in the y direction, weight is going to have a negative value because it is pulling down in the negative y direction. Okay, so let's substitute what we know. We know that the force is just ma, and this is in the y direction. It is equal to the normal force. Well, there's only one. It's in the y direction. So we'll just call that n minus, and we're going to replace w with mg cosine theta. Okay. Over here, we see that acceleration in the y direction is present, but we know from our drawing and common sense that this child is not moving in the y direction. He's moving in the x direction. So this is just going to go to 0, leaving us with n minus mg cosine theta equals 0. All we have to do to solve for the normal force is rearrange, and we'll find that the normal force is equal to mg times the cosine of theta. And this normal force is in the y direction, so don't forget your little y hat. So that would be the final answer. Thank y'all for watching.